Hello, everyone. I'm Qin Huang from Peking University. Today, it's my pleasure here to present our paper. This is a joint work from Peking University, Chinese Academy of Sciences, the Chinese University of Hong Kong, and Microsoft Research. In this paper, we address flow level monitoring. We consider a typical network. There are some end hosts in the network, and they are connected by switches. All end hosts and switches can execute some monitoring tasks. There is also a centralized controller in the network to manage all the end hosts and switches. For each packet in the network, we abstract it as a key value pair. The key identifies the flow this packet belongs to, and the values indicate the information carried by this packet. The goal of flow level monitoring is to group packets into flows based on the flow keys and compute various statistics such as packet count, byte count, and so on. Network administrators usually hope the monitoring to be highly accurate, and at the same time, they also want to keep the resource usage limited. In previous studies, we often need to make a trade-off between these two objectives, but in this paper, our goal is to achieve both full accuracy and resource efficiency. For full accuracy, we expect the monitoring can cover all time intervals, all devices, and record all flows. And for each recorded flow, we also expect that its statistics are computed with zero error. Such full accuracy can benefit many network management applications because full accuracy can avoid noisy interference due to measurement error. So eventually, the efficiency of network management will be improved. For resource efficiency, we observe that each type of entities in the network have its unique resource limitations, and we need to avoid resource overload in all of them. For end hosts, they have sufficient memory and their CPUs provide great flexibility to realize arbitrary processing logics. However, we need to control the complexity because the CPU is a bit slow when processing the high-speed network traffic. In addition, end hosts have limited visibility. They have no information about the network internals. For switches, they can process traffic at line rate with the switch ASICs. However, the memory in switches is limited and there are many restrictions on their programming models. For the controller, it can integrate resources from multiple physical servers to form a cluster. It also has the global view of the network. However, the link capacity between the controller and each data plane device is limited. So we cannot transmit too much traffic to the controller. Given the various and tight resource restrictions, existing approaches often make a trade-off between the resource efficiency and full accuracy. One extreme is classical SNMP techniques. They consume very few resources, but they are too cost-gram to provide accurate results. Another extreme is hash table. Hash tables achieve full accuracy by exactly tracking each flow. However, per flow tracking exceeds the memory capacity of switches, so hash tables can only be deployed in end hosts. Between the two extremes, there are many approximate approaches that trade off accuracy to reduce resource overheads at different levels. For example, sampling, event matching, and topic counting reduce overheads by only considering a subset of flows. However, their results are not complete because a large number of flows are missing. Another class is sketch. Sketch techniques allow multiple flows to share counters to reduce memory overheads. However, its accuracy remains approximate due to the flow conflicts. Different from these approaches, our goal is to achieve both resource efficiency and full accuracy at the same time. Before presenting our design, we first analyze the root cause of the resource accuracy trade-offs. We find that existing solutions usually deploy operators in data plane devices, including end hosts and switches. This is a common approach to reduce the overhead of the controller. However, the operator in each device is executed individually and lacks of collaboration. For example, an end host cannot control the processing behavior in any switches. In this case, the operator in each device has to contain complete functionalities, such as flow extraction, value checking, and resource allocation. This makes the operator very heavy, so they have to sacrifice accuracy to fit the resource limitation of the devices. This also motivates us to optimize the tool design choices in existing solutions, heavy individual operators, and limited collaborations. So in this paper, we present OmniMon to achieve both resource efficiency and full accuracy. Our key idea is to redesign the underlying architecture of flow monitoring. Instead of deploying the complete functionalities in each device and executing them individually, we collectively employ all entities in a network to build a distributed telemetry system. In particular, we consider the following two questions about the architecture. These questions are raised from the perspective of distributed systems. The first question is how to distribute network telemetry across different entities and coordinate these entities. And second, as in many distributed systems, we need to deal with some unreliable issues such as inconsistency and message loss. This is necessary to guarantee our telemetry architecture works correctly. We first consider the first question. Our answer to this question is to follow the split and merge principle to propose a novel distributed architecture for flow level monitoring. We divide the network-wide flow monitoring into 4 partial operations. Each partial operation is responsible for a piece of monitoring logics, and this breaks the heavy individual operators in traditional solutions. Then we coordinate the resources of all network entities to realize these partial operations in a distributed manner. The coordination ensures that the 4 partial operations will eventually form zero-error results, and at the same time, the resource consumption is limited in each device. So both full accuracy and resource efficiency will be achieved. Now I will introduce how these partial operations are realized one by one. For flow tracking, we observe that we only need to record each flow once in the network. Thus, we record the key of each flow in its source and host. For value updating, we track them in both end hosts and switches. In each device, we allocate some slots of counters to store flow values. And there are 2 types of slots designed for egress traffic and ingress traffic, respectively. When a packet arrives in a device, we select 1 or more slots and then update their values based on the packet information. The third partial operation, flow mapping, determines how a flow associates with its slots. Since the resource constraints in end hosts and switches are different, we employ different strategies here. For end host, each flow has its dedicated slot because the memory is sufficient in end host. Since the flow keys are checked in the source, we organize the flow keys and egress slots as a hash table. But in destination, flow keys are not checked for incoming traffic. So to resolve this problem, for each flow, we embed its location in the hash table in the packet header. Then the destination host can extract this index to locate the ingress slot. In switches, since the memory is limited, we allowed multiple flows to share a same slot. This is similar to Sketch, but Sketch algorithms compute slots by hashing the flow keys at switches, and our approach is different. We compute the switch slots by coordinating the controller and end hosts and not in switches. Since the controller has global view of the network, this can significantly reduce the conflicts at switches. And when the switch indexes are computed, they are recorded in the hash table in the source end host and also embedded in the packet header. Each switch extracts this index and updates the corresponding slots with the packet. And the final operation, collective analysis, is performed in the controller. It collects the results from all end hosts and switches to form the final flow statistics. Since the slots at the switches can be shared by multiple flows, to achieve full accuracy, collective analysis needs to restore flow values from the shared slots. Recall that in each end host, we have recorded flow keys and flow values with zero error. So our basic idea is to decompose the shared slots in switches with the aid of end host information. Here we present an example. In this example, we consider a switch slot with value 24. This value must be contributed by multiple flows. Fortunately, we have recorded flow keys and flow values with zero error at each end host, and we also record the switch index for each flow. So we can find which flows are actually mapped to this slot. In our example, there is a flow 1 with value 13 and a flow 2 with value 11. So we can decompose the value in the switch slot into the two flows according to the source information. So far, we have introduced all the four partial operations. In summary, the resource usage is acceptable in each type of network entities to achieve full accuracy. In end hosts, the memory is sufficient to host hash tables, and the hash operation is acceptable for general CPU. In switches, we only extract switch index and update counters. Both operations are supported by commodity switch ASICs. For switch memory, since we let flows to shared counters, the memory consumption is also limited. And in the controller, we mainly leverage its global view to allocate slots and perform collective analysis. Now let's move on to the second question about the reliability guarantees. In this paper, our architecture faces two challenges from the unreliability network events. First, network monitoring is usually executed based on time intervals, but we do not have a global clock to synchronize time intervals across devices. And second, packet loss is common, so the flow values may be not recorded in some devices. In previous studies, these two issues do not become a big problem because previous studies have limited network-wide collaboration. However, in our system OmniMon, we need to deal with them, otherwise the architecture fails to work correctly. Here we present an example to illustrate the impact of the two reliability issues. Here we have two flows with their values 13 and 11 respectively. These two flows shared a counter in a switch. Ideally, all values of the two flows should be recorded in the switch, so the expected value in the switch is 24. However, if some packets exhibit long network delay, part of flow values may be included in different intervals after the long network delay. And another case is packet loss. With packet loss, some values are even not recorded in the switch slot. And in both cases, the value in the switch may be long. And in our example, the value in the switch is now 20. Since there are multiple flows with long values, we cannot decompose the value in the switch because we do not know the actual contribution of each flow. We propose two mechanisms to address the two challenges. For the lack of global clock, we propose a hybrid consistency model to synchronize time intervals. By hybrid consistency, we mean that it is a strong consistency in most time, but will be degraded to weak consistency at some times. Similar to our architecture design, the hybrid consistency also coordinates all entities in the network to synchronize the time intervals. It provides two guarantees. First, each packet is guaranteed to be included in the same time interval by all devices in its path. And the second guarantee is that all end hosts reside in the same time interval in most of the time. For packet loss, we propose a linear system to infer the loss, and we also propose a flow mapping algorithm to make the linear system correctly works in general cases. Since the time is limited, I skip the details here and you may find more results in our paper. We build a prototype of OmniMon with DPDK and P4. We conduct trace-driven evaluations in both testbed and simulation environments. We first measure the host overheads. We compared OmniMon with packet-gen that is also implemented by DPDK. Since packet-gen has no monitoring functionality, we use it as the baseline to measure the overheads of OmniMon. In the left figure, we can see that even when we add the end-host monitoring functionality of OmniMon, the throughput drop is less than 10% compared to the original packet-gen. In the right figure, we profile the overheads. We find that most overheads comes from hash lookups, but the overall CPU resource spent in each packet is less than 40 cycles. The second experiment measures the switch overheads. Here we compare OmniMon with 4 recently proposed sketch techniques. Each sketch technique only monitors packet count in our experiment, and we have 2 versions of OmniMon. One simple version monitors packet count only, like the sketch technique, but another full version monitors 9 types of statistics in one configuration. We observe that OmniMon consumes much less resources than sketch techniques because it does not perform hash functions or record flow keys. And OmniMon can achieve full accuracy, but the sketch techniques only provide approximate results. We have more results, more experiment results, and you may find them in our paper. And to conclude our work, we propose the OmniMon architecture with 2 guarantees on the consistency and accountability. And we build a prototype and conduct experiments to compare it with 11 state-of-the-art solutions in various aspects. And our source code is available now. And that's all of my talk. Thank you for your attention.